So good afternoon, everybody. It's very nice to see you all around. And so today we have the pleasure to have Claudia Draxl from the Humboldt University of Berlin. She's a professor in condensed matter theory. She has been working on many topics, and one of the topics that is of interest for us today is like this machine learning and big data for material sciences, where she's actually the chairperson of the NOMAD laboratory, which is this novel material discovery laboratory, which explores like data-driven research based on big data in material sciences. And so the floor is yours now.
Yeah, thank you, Alexandra. I'm happy to be here, and as I see, I've chosen a topic that's about similarities and patterns in big data of material science, and I'll come to this more specifically in, I don't know, a few minutes or 20 minutes from now. But first, I would like to put all this in a bit bigger context, to draw the bigger picture, and just asking the question, what do we need this for? Why are we interested in similar materials? Why would we like to identify patterns in big data and things like that? So starting with materials and talking about similarities, I start with something very, very simple that you all know. So these are two materials, diamond and graphite. And they are very similar in one sense, that they're all based on carbon atoms, nothing like this, but they're also very different in nature, because as you see from the transparent nature of diamond, it is a very wideband semiconductor, whereas graphite is metallic. Diamond is the hardest mineral we know, graphite is extremely soft. So how come that two materials that are very similar in one sense are completely different in another? So it's not only the atomic composition, obviously, that counts, but it's also the arrangement of the atoms, which play a very big role. And there you see in diamond, you have this very highly symmetric cubic cell. Graphite, on the other hand, is built of two-dimensional planes that have hexagonal symmetry, and they're coupled very weakly to each other. It's just van der Waals bonding. So, and this very weak coupling that also allowed people, Moselov and Geim in particular, to create atomically thin layers of this, because you just need to take a Scotch tape and then you can peel off from a pencil, for instance, these very thin two-dimensional layers. And this was the birth of, was not the birth of graphene. I think graphene was known before, but at least this Scotch tape technique made it very famous. So, but you can also do other things with this. You can just take such a sheet and to wrap it up, again giving rise to very different properties depending on how you wrap it up, or you can create out of carbon atoms even these very big molecules. These are C60 buckyballs that again have very different properties. So just playing with the geometry obviously gives us a handle on how to create materials with very different properties. But of course, we have now the toolbox of all kinds of different elements that we combine, and just looking at the periodic table of elements gives us an idea that there is basically an unlimited number of materials, because you can combine everything with everything, and not only in terms of composition, but again, in terms of geometry. And this is nice because we're all working on this to find materials and to characterize materials that may be useful for one or the other application. So for instance, we need very hard alloys, for instance, for our tools. We need transparent semiconductors for, not only transparent, but semiconductors for our gadgets like iPhones or for screens. We need lightweight materials for transport properties. We need light emitting materials, or we need also materials for things that we probably don't think that it's a genuine material science problem, but also in medical applications like artificial teeth or hips or so. That's a problem of material science. So The question is, of course, that it's urgent. We need, of course, not only that we want to improve. This is somehow the nature of people to get better and better. But we really need to get better in order to solve our problems of environment and energy and so on. So how to create materials with, let's say, relatively high speed that fulfill certain properties that we want to have done. So, and we can do, of course, the natural way, like we are doing. And this brings me actually to the research paradigms that we are working with. So we can either perform experiments. That means we do this make and measure principle. So we create a sample and we measure the materials and to find out what the properties are. Of course, we can also enhance this by theory. So what the second paradigm of research, material science research, is the theoretical science. And this is based on the laws of classical mechanics, electrodynamics, or what you see here on top, the famous Schrödinger equation. This is basically the workhorse of computational material science, which actually has been established in the last decades as a paradigm of its own. And why is so different from just paper and pen work of the theoretical science? Because we can kind of make a combination of these two by performing computer experiments. So we can dream up any material on the computer, and then we just see what the properties are. And of course, we need new methods for this. So solving the Schrödinger equation by paper and pen wouldn't work. Actually, we know that it can only be solved for the hydrogen atom, and otherwise it's an NP-hard problem. So, and this was the birth of density functional theory, and also methods like molecular dynamics, Monte Carlo simulations, in order to perform these computer experiments. So far so good. This is what we're doing in our labs every day. So my group, for instance, is somehow focused in between this second and third paradigm, with a stronger focus on the computational part. Anyway, but of course there's something new coming up now, and I just mentioned before in the informal talk that looking at the program of the APS March meeting of this year, I found 51 sessions that were dedicated to machine learning, big data, networks, deep networks, and things like that. So obviously there's a fourth paradigm up and coming, I would say, and this is data-driven or data-centric research. Actually, it has not been invented for material science, so the general term was coined in 2007 by Jim Gray, talking about discovery by data. And of course, I think computational and those experimental material science, both of them are prone to that because we create a lot of data. So both experiment and theory creates a lot of information that is so far not optimally exploited, because only part of the knowledge that we extract from our daily research is finally published, and a lot of stuff it's getting lost. And this brings me actually to the point that we could exploit the data, and by somehow creating novel tools of artificial intelligence and machine learning, we could gain a lot of knowledge from the data that we create anyway. So now, getting back to this transparency that I've just shown, we could somehow now think to replace this periodic table element by another chart or a map. And this map will tell us, in the future at least this is our dreams that we have written down in this publication together with Matthias Schäffler, that at some point in time, we should have maps available that tell us where in the space, material space of composition or structure and the geometry, we could find materials for certain applications. So where in the material space do we find good superconductors? Where do we find good photovoltaic materials? Of course, such a map will never be two-dimensional, so the material space is much too complex and complicated to be plotted like this. So it will be a very highly dimensional representation of the materials. And in particular, we have to find out what the driving force behind a certain property or function is in order to be able to do so. But at the end, this is the vision where we like to go, right? And this brings me somehow to two topics. One is just back to the title about similarities, because in such a cloud here, we will find materials that share some properties, so that they have similar properties, so they should share the properties of being a superconductor. Here they should share the property of being a photovoltaic material. The question is how we find them. This is another thing. I probably come back to this a little bit later, but I first would like to ask the question: what is the prerequisite of going in this direction? What do we need in order to do so? And this is, of course, to create new tools of artificial intelligence that help us to explore the data, but we also need the data. And we need the data in a form such that we can make use out of it. And that's why I would like to briefly sketch in a few minutes a project that we just started here in Berlin, and not only in Berlin, but all over Germany, that is dedicated to building an infrastructure that provides the data that finally will help us to establish the first paradigm of material science. So, in short, the project is called Fearmat. Fear stands for the FAIR principles, so findable, accessible, interoperable, and reusable. And this MAT stands for condensed matter physics and the chemical physics of solids. And it's a project that's funded, got funded recently. We started in October last year, so 3 months ago. And in a nutshell, you could say it's an all-inclusive user-driven approach to develop easy-to-use tools and an infrastructure towards fair data processing, storage, curation sharing, and AI readiness for future use of materials data. So it's a bit dense, right? So, and what is written here in one sentence actually is a lot of work. And I'll just sketch you probably in a bit more pictorial way what I mean with that. So first of all, user-driven approach means that we need the community behind, because only the community knows what the data are about, what they mean, and what they should be good for. All-inclusive means that we should not just look at calculations or not just look at experiment, but we need to bring together data from all the different subdomains and fields. So we're covering synthesis, experiment, and theory. And yeah, to keep it short, what you see here on the left, ABC, are these 3 areas. So these are the people basically sitting in the labs. And these people already now, they create a lot of data, either by measuring something or creating a sample or carrying out a calculation. And what we like to do is to provide them tools that help to process the data such that at least locally the data can be harvested in databases. So overall, it will be a federated data infrastructure, because we cannot ship all the data of all Germany or all over the world to a single place. So there should be data hubs, so to say, either in different labs or computer centers. But most important, even if these data are stored locally, we need to put the information about the data together in a central place. So in other words, the metadata, so the description of the data, they will be stored centrally in a central database, such that we somehow have all the information about the possible data available, and even can trace back to the raw data if we need the raw data. And so this will then help us to somehow to provide all the information of all researchers from all the different fields together. And what looks here like public viewing is kind of the let's say, the aggregated information about all the research results that the community has created. And this will be then available to the scientists themselves, of course, because we need all this again. So people sitting here, but also engineers and companies or pupils, students could look this data up and could see what the information is inside the research data that we have. So that's the big picture. And of course, you could tell me now this is much too complicated, because how could you do? There are thousands of people working on very different aspects of material science. How can you really bring together data in a meaningful way? And so we're searching for commonalities, right? So we cannot build a database for semiconductors, and we cannot build a database for the synthesis of alloys or something like that. So we must find things to exploit synergies. And we came up with themes, recurrent themes that all of us share. So these are, for instance, these are 5 in total. So let me start with the first one. It's metadata, anthologies, and workflows. So that means that in order to reuse data, we need to describe them in a meaningful way, so and in the most complete way. And that means that metadata are the first crucial step in order to fulfill our goals. And then we can combine, or we can see what the relation between these metadata is, put them into ontologies, and ideally, of course, we also should store and make use of the workflows that have been used in order to go to this data. So starting from the sample, from the creation of the sample until the measurement, for instance, we have to follow basically all the paths that scientists are going. Actually, metadata is the foundation of fairness, because if they're not described, they are they're not really meaningful to ourselves or to others. Then there is 4V challenges of big data, means velocity, veracity, variety, and volume. And this hits all of us, but in a different way. So some data are very voluminous, and other are struggling with veracity or variety, but all of us have to deal with this issue. Yeah. Then very important are parsers, normalizers, and converters. So what does this mean? I mentioned before that we are pursuing a user-driven approach. That means we don't want to somehow put the burden on the users. They have to fulfill certain rules and standards and so on, but we would like to support them. And supporting means that we have to create the tools that help them to read out data from an instrument or from a code, for instance. This is what concerns the parsers. People don't need to care about in which units their measurement is performed, their calculation. This is what the automatized tools should do. And also converters. If one person likes a lab notebook better than another, and it's different for another person, we shouldn't bother them, but we should make sure that we can somehow translate all these tools into each other. It's very important to get the community on board, or to keep the community on board. So people need support for what they're doing in this sense. Yeah, and then this brings me also to the main topic of today, is data curation and quality assessment. Because if we really want to go for this big picture, that we want to bring together data from very different people, from very different fields, then we need to make sure that we don't mix apples and oranges, but really bring together only data that are comparable to each other. And for this, of course, we need to know the data quality yeah, this is interoperability is, I think, besides the metadata, this is the most crucial issue of having fair data and fair databases. Yeah, last but not least, I mentioned this public viewing before. I mean, to just store data for uploading and downloading them, this is very useful for those who are experts. So if you want to carry out a calculation with Abinit, you like to find other calculations with Abinit, and then you can compare input and output files. But if you're an engineer or an experimentalist or a guy synthesizing samples, you probably don't care about the input file and numbers, but you would like to see what people have calculated or what people have measured. In that sense, what we call the nomad encyclopedia, materials encyclopedia, is important to see what the results of the community are. And likewise, for reusing data, we also have to provide tools that help us to analyze data and to learn from this data. So, and with these recurrent themes in mind, then we can actually approach the different areas that we have in mind. And just in brief, what are they? I mentioned synthesis before. Synthesis is something where hardly anything is digital so far. So there's only a very few attempts of collecting data from synthesis and synthesis recipes. And we like to go along 4 different synthesis routes. So from the melt, gas phase, solid solution and assembly to make synthesis data fair and to make synthesis reproducible, because only if we describe our synthesis process, data will be reproducible there. And we'll come up with a reference database for crystal growth. Most important is then to bring together the data and the tools from synthesis and experimental characterization to also bring together theory and synthesis, because probably with artificial intelligence we can also learn faster how to synthesize samples in a reproducible and the best way. So in short, what about experiment? I mean, you all know that there's so many different ways of characterizing experiments. So if you have samples, so if you have a sample underneath here, then there are what this cone symbolizes. There are many experimental techniques to measure materials properties. And I just picked out 5 here because these are different experiments that we are starting with. So we start with electron microscopy, X-ray, photoelectron spectroscopy, angle refold photoemission, atom probe spectroscopy, and optical spectroscopy. So these are different experiments that are different in nature. They have very different subtleties also regarding processing without the and the 4V of big data. So some of them have a lot of data, like electron microscope, for instance. In optical spectroscopy, it's not so many data, but there's a lot of variety and veracity, as I'm going to show you in a second. Before that, just let me summarize what we're planning to do is, so we would like to establish metadata and workflows for these very extremely diverse characterization methods by the community. And we also like to support the community with lab notebooks and laboratory information management systems. Now, let me get back to optical spectroscopy. What I like to show here is the problems that we see when bringing together data from different sources. So if you measure something or if you compute something, then in the ideal world, you would assume that all measurements on all samples of the same material should give you exactly the same. So unfortunately, our world, or maybe fortunately, I don't know, our world is not ideal. And the picture that you see here on top, this demonstrates this very clearly. So this is the dielectric function of silver. And silver is the most simple material you can think of. It has one atom, and it's elemental solid, but it's also a noble medal. So you would expect that this is a perfect example for creating benchmark data. Right? But if you look at these different measurements here, then you hardly can believe that this is the same material at all, because these peak positions, they differ not only by milli-electron volt, but by electron volt in some of them. Right? So how come? And then we have to deal with, let's say, two main aspects. One is that obviously what people call silver is not always the same. So there is a lot of impact that comes from the quality of the sample. There could be contamination, there could be defects, there could be whatever. And the other aspect comes along with the measurement. Right? So first of all, there are many ways of measuring one and the same property. So optical spectra, I can obtain either from ellipsometry, from absorption, reflectance, or electron microscopy. Interestingly, none of them does give you this, this spectrum directly. So there's always some transformation step involved, but there's always some approximation involved by interpreting the raw data. And of course, all of this comes with a certain uncertainty, veracity, right? So we have the variety here that comes from the different measurement techniques, but each of these techniques comes with some uncertainty or veracity. And then, of course, you always have to deal, even if you, with the fact that even if you stick to one method, there are many instruments that come with different resolution data formats and whatnot. And last but not least, of course, I can also compute all this. And also for computing the dielectric function, we have several or many different methods with different levels of sophistication. So bringing these things together is really gives us a headache and a nightmare. And now I can show you something that is a first step in this direction, or a first success story, if you like. And this is the Nomad laboratory. We call it a laboratory because it consists of different apps in different aspects. And this Nomad laboratory, it started actually in 2000, and probably 10 years ago we started with that. And in 2014 we made it open, so it's a data repository for computed data. 2014 means it was a fair database, or created as a fair database before 2 years before the term fair was published. Right? So what it's about, people from all over the world can upload calculations from electronic structure theory. And since 2014, we're collecting more than 100 million calculations. So these are the raw data. So people basically up and download their input and output files. Now, there's a lot of variety because the community uses about 40 different codes that you can see here. So these are the uploads, most uploads at a certain point in time, right? And this also tells you that, of course, 100 million calculations are not computed by one person and not by one code and not by one method. So that means that, of course, also all the results come with a lot of veracity because people use different computational parameters, different units, different fine formats. And what we have in the archive now is kind of a normalized form where everything is brought to the same units and file formats. And of course, we had to use it to develop a parser for each of these codes. Now, the encyclopedia is also a forerunner to this public viewing that I've shown you before, so where you can already see what people have computed all over the world. And the artificial intelligence toolkit is also a collection of tools that people can use to analyze the data, to learn from the data. So everything like this is basically a first step towards what we're doing right now, planning right now, including now starting to include also experiments and data from synthesis. So, and this brings me to the third part, so to say, also theory. We have just seen that the Nomad laboratory already has a collection of data. It's a forerunner to this, but of course we cannot stop here also in terms of theory, because there's a huge variety of other methods. And these are, for instance, classical simulations that come with a lot of volume, because all these trajectories of molecular dynamics, if you think about. And there are also very highly sophisticated quantum mechanical many-body techniques to describe excited states. And so the idea is, first of all, or this is what we are doing or have done already, to integrate this nomad laboratory into this new big data infrastructure, to enhance the services, but then also include a lot of other methods, like molecular dynamics, Monte Carlo simulations, and theoretical spectroscopy, for instance. Yeah, to wrap this up, now we built this data infrastructure for synthesis, experiment, and theory. And in order to do so, we have built a data center in Berlin, here at the Humboldt University, for material science data. And the idea is that all the people that are employed, or most of the people who are employed by this project, they come together here and they work together on this very big data infrastructure. So these are people from computer science, from informatics, from physics, from chemistry, from theory, from experiments. So all of them, they work together in order to build up the this data infrastructure that I just discussed with you. Now, finally, I get back to the title of this presentation, which was about similarities and patterns in data, right? And let's say the link to what I just said before is that one of the links that now we have, if we are successful, we have all the data from all over Germany and probably all over the world from all different areas. So what can we do with this data? We want to learn from them. We want to use artificial intelligence, but we want to apply artificial intelligence on data that we understand. Because even if you have a world-class methods, AI method, it doesn't help if you train this method on data that are not worth to be used. And in that sense, we have to understand the data, we have to understand the quality of the data, and we have to make sure that we obey the fair the interoperability. And now, this brings me to back to similarity first. So why similarity? I mentioned before already that we would like to find materials that are similar to each other in one or the other way. For instance, all of them share the property that it can become superconductors, or all of them share the band gap or whatever, right? So, and for this, we have implemented a toolbox that measures or can measure, so to say, similarity. And one of the, let's say, examples that I want to present here, or the most important example I like to present today, is the so-called density of states fingerprint. So we compare materials in terms of the electronic structure by looking at the density of states. So we follow here, already started actually by work by Saif and then in Cotarola's group, but we have further developed it in the sense that we can focus on very specific features. Now, let me explain to you. Here we have a density of states, right? And then we divide this energy range into intervals, and these intervals can be denser in some area we want to focus on and can be wider somewhere else. So we can weight basically the region that interests us most, and we can also select an energy range in total. Then we integrate the density of states inside these little intervals, and we assign each interval a value, and this gives rise to this fingerprint. So with this weighting procedure that I mentioned. And now we can compare these fingerprints of different materials. Right? And we do so by showing an example by the similarity coefficient that was introduced by Tanimoto. It measures the similarity between two different such fingerprints. If it's 0, they have nothing to do with each other. If it's 1, these are identical, and everything else is in between here. And I like to exemplify this with the example of a simple example, gallium arsenide, that we have chosen as the reference material. And then we look up all the density of states of 280,000 materials in NOMAD and look which of the material is closest to gallium arsenide. And this is the result. Now, closest to it is gallium phosphide. It has a similarity coefficient that it's high, but it's smaller than 1 because we see here that the conduction bands are shifted with respect to each other. But if you're just interested in the valence band region, you could say they are basically identical here. So gallium phosphide could replace gallium arsenide. Well, if you're a semiconductor physicist, you could say, okay, of course, I know this, that this was to be expected, but maybe you would have expected that this material also has a very high similarity coefficient and basically shares the valence band structure, not in the very low end and not in the conduction band region, but here in this region, they're actually very similar to each other. And I think this is something that would be nice because, I mean, gallium arsenide probably we don't need to replace, but think about solar cell materials. Now, what really enters or has entered the market already are the hybrid perovskite materials. And these perovskite materials, they're all toxic, they contain lead. So probably would like to find materials that have very similar characteristics to them, but don't have lead inside. So in that sense, such fingerprints could be really useful to identify materials for replacing one material that is critical in one or the other term. So that's one thing, and this is actually where we started from, to find materials that are similar to others. But now we were thinking that you could use this fingerprint also for something completely different, and namely for assessing data quality and for learning errors of data. So we exactly use the same thing, but now we, as I say, we explore what the impact of a parameter or a method or whatever could be, right? So again, I exemplify this by a simple material because we wanted to see basically how the result of different calculations for one and the same material are. So silicon, space clock 227, highly symmetric, we found more than 2,600 calculations in the NOMAD database. And again, so in the best possible world, all these calculations, if computed for the same geometry, would be identical. Right? Of course, experience tells us that's not the case. And I would like to show you two examples now, what the impact of a certain, let's say, a parameter is. But first, let's look at the distribution of data. So there are many codes actually that have contributed to the database here. So on the left, you see an example, density of states of silicon, where they have the code and the computational parameters in common. So these are both exciting calculations, but here they differ in the method. And what you very clearly see that similarity coefficient is high, but it's not as high as you would anticipate from the valence band structure because they are basically identical. But you see the difference comes from the conduction band. And again, if you're an expert in the field, you would say, okay, fine, I know that the GW approximation shifts the bands to higher energies. So, but of course, the machine tells you that this is the impact, right? So you can measure the impact here. Huh? So in that sense, we can measure the impact of methodology, but you can also measure other things. So for instance, now we have an example where we have the same method. So both are gradient corrected functionals of density functional theory, but now we have two different codes. And again, the similarity coefficient is smaller than 1. It's better than before, but it's smaller than 1. And here, of course, you could think the first idea would have now, of course, FHR Ames is an all-electron code and WASP employs a pseudo-potential. So obviously, or the first obvious reason could be that the impact of the potential could make the deviation in the similarity coefficient or from each other. So, but we can also go further now. We can also, well, stay with codes and functionals here, but do a different analysis. So what I show here is the similarity matrix of calculations for aluminum. So again, we have a very high number of such calculations, more than 800 in the database. And then we can somehow explore patterns in the similarity matrix, right? So here we compare the similarity of each of the calculations with any other. And of course, this would give you any pattern unless you order these calculations. And in this case, I order them such that I have, well, we find out that these 800 calculations have been computed by two codes. It's FHI aims and VASPs, and two functionals. So altogether, we have only 3 combinations, which are FHI aims calculations with 2 different functionals, GGA and LDA, and all the VASP calculations are with GGA. And now I order these calculations such that the first 300 or so are from the first kind, the second 300 from the second, and the last from all VASP calculations. And then that means, of course, that inside such a block, the calculation should be very similar to each other, and this is exactly what we see here. We have a block here of FHI aims GGA. Then you see another block here. These are also aims LDA calculation, and then we have a third block here, which don't have so much in common with the FHI aims calculation, and these are VASP calculations. So obviously, we can somehow see a trend of similarities depending on the code and depending on the functional. But we could also group this data in a different way, namely in terms of computational parameters. Because in the example before, we didn't care about parameters, we just looked at the code. Now we group these calculations according to k-points. Now we have one calculation with a small number of k-points. This actually gives you this very small matrix here, and this tells us this matrix has nothing in common with all the other data. Or in other words, obviously, this number of k-points, it was 32, is much too low in order to produce reasonable results. And then you have, you see, depending on this, if you increase this k-points, you see patterns. So small number, larger, 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 larger number. And I like to focus on this range here, because here you see that all these calculations from the color code, you see that all these calculations are very similar to each other. What is interesting here is that this could be calculations with a relatively small number, let's say 300 k-points, or an extremely high number of 2000, but the results obviously are already the same, or nearly the same, right? And this tells us, obviously, that this last block shows results that are already converged. That means it doesn't matter anymore if you increase the k-point number, the results don't change anymore because you have reached the convergence. So, in other words, we can draw backward conclusions about the convergence of results by looking at the similarity matrix. So, and then if you're wondering why you still have blocks inside these matrices, of course, because here we only have grouped the results with respect to k-points, but of course, inside these groups, you could find then some blocks here that pop up because they have been computed with one of the same methodology. So far so good. All these calculations are fine, but this analysis helps us basically to understand the data. Now, I have 2 more examples to share with you, and again use the same idea of fingerprinting, but now we go to optical spectroscopy. I show you some exciton spectra in boron nitride. So boron nitride is a layered material that you see on the right. then we have the equation that we have been using for creating this data was the beta-cell-beta equation of many-body perturbation theory, so that explicitly treats the interaction between the electron that is exciting during shining light on this example and the hole that it creates. So shining light on the sample means that we create a hole somewhere, and then by looking at the electron hole wave function for a given coordinate of the hole, we can basically see what the distribution of the electron around the hole is. And this is what I'm going to show you, right? So on the left, I will show you the spectra. On the right, you see this electron hole distribution. So now this spectrum has been created with, if you look at the sum here, by a k-point mesh, like in the example before, of 3 by 3 by 1. Right? And then you get this result. That means in every second layer, we see a homogeneous electron distribution. So the question is this good enough? Is this the result? And the question, the answer is no, because if you increase the k-mesh, doubling in all 3 directions, you see very strong changes, and the similarity coefficient between these two is only 0.18, so very small. And the reason is, if you go back here, is that now the distribution of electrons in this every second layer is lost, but we only have distribution of electrons in every 4th layer. So the exciton wants to be more localized. Is this enough? Again, we say no, because now the similarity coefficient is getting better, but still it's not perfect, because now we see that the electron hole distribution is even more localized, so it only stays in one plane. And now we can increase further, and nothing changes anymore, because now we have already found the converged result. So again, we can somehow relate the similarity with the finding the physical results, such that we understand actually what we see and what we measure on the left, that we also understand in terms of the physics. So, and the last example I would like to share with you is something going even beyond. Now we stay with this density of states fingerprint, but we combine it with unsupervised learning. Because if you think back to the first example, or to these clouds of properties that I've shown you at the beginning, if we have big data, we simply want to explore what we can see, what trends and patterns we can find in the data without asking a specific question before. So we could just like to explore a data space. And now, to do so, we explored, in this case, not the nomad repository, but we went to the computational 2D materials database from the DTU in Denmark, where we found more than 4,000 structures and more than 3,400 density of states. So again, it's a large playground for just finding something. So we, as an unsupervised learning method, we use the clustering algorithm. So we tried to find out clusters of data, and inside these clusters, the data should be comparable to each other, very similar to each other. So, and if you do so, and finding clusters of similar materials, and defining this threshold, so when we define a material similar to each other of 0.75, this is what we find in the whole database. So there are many clusters that only have 2 members, 2 materials to being very similar to each other. And then, of course, if you want to have many materials to be similar to each other, you don't find so many of these clusters, but still there are some clusters, they even have 11 materials inside. Now, this is again a similarity matrix that it's ordered or sorted according to these clusters. So these are, for instance, clusters of materials that have 6 members or more than 6 members. And there you see that, for instance, these 2 clusters, the first 2 clusters, they still have some similarity to each other, because here the similarity coefficient, if you look at the color code, is still pretty high or relatively high. Whereas, for instance, if you pick out this cluster, then you will realize that it basically has nothing in common with this cluster here. So it's all 2D materials, but obviously some of them are more similar to each other than others. And I just would like to show you one example now. This is a cluster of 5 materials. Here you see the density of states of these materials, which are indeed very, very similar to each other. And so let's explore now what kind of materials these are. So if you look at the structure and the composition, then you see that all 5 have the identical crystal structure. So they're all transition metal decalcogenides, these layered materials here. And you see also that all of them have 8 selenium atoms. Then all of them have titanium atoms. But from this material, let's say here we have 4. But out of these 4, either one of them or 2 of them have been replaced by either zirconium and hafnium. Yeah? So they share the crystal structure, and what else they share? If you look at the periodic table of elements, then you see that zirconium and hafnium are just in the same column as titanium. So what we have basically, what the machine or this clustering algorithm has found, it has identified 5 materials that are isoelectronic to each other, and this together with the crystal structure makes up for the high similarity. At the end, what I think is equally exciting is that we also find outliers. Because, I mean, if you really want to make progress, then possible just looking in the material space that you know for finding something that is similar to those that you know already would not really push the field forward, because you can only make incremental steps. So probably you would like to predict something that is completely outside this material space you're looking at. And in that sense, identifying outliers in such pattern is really important. And I don't know if these materials are useful for anything, but I would like to convince you that this is an outlier that we have found. So these are 2 materials that have a very similar electronic structure in the whole energy range. We've looked it up. But now if we analyze these materials, we see they have completely different crystal structure, and they also have completely different species. So they neither share the composition, nor they share the structure, nor the symmetry. So in that sense, it's really, it's a pure coincidence that they are similar. And now we have verified this. So the similarity coefficient is pretty high, but now we have verified, if you look at these band structures, they're really completely different. But somehow, by integrating up all these different bands, you come to the same fingerprint without really finding similarities in the origin for this. And so in that sense, you really could call this an outlier. And I think this is, as I said, I don't know whether this material is useful or not, but it tells us that such unsupervised learning approaches could help us to identify things that we wouldn't have expected. Yeah, this brings me to the summary and an outlook. So what I wanted to show you is that we've designed new approaches to explore available data spaces, to measure similarity that could be either used for finding materials that are similar to others, or to assessing data quality or the impact of methods, computational parameters, and the like. We have validated this approach by our domain-specific knowledge. And the next steps, as I mentioned before, are extending all this data space and also the tools to experimental techniques. The way we're going to do this is written up in a paper that's actually to be, should appear soon, is accepted in Nature. And this brings me back to what I've shown you before, the new project that we've started, which somehow combines synthesis, experiments, theory. We built a data infrastructure. We will reach out to the community, demonstrate that's useful in demonstrators, but also provide training and support. And yeah, with this, I would really like to thank you for your attention.
Thank you very much. I will stop the recording now.